Hello, welcome to Advanced Composites. Today is the beginning of the third week of this course, and what we will cover over the period of this week is that we will learn how to develop stress strain relations, not necessarily at the ply level, which we had discussed in the last week, but at the laminate level. Now you know that a laminate is basically a collection of several layers of composite materials. So you can have a laminate which has 10 layers, 20 layers or whatever, and what we are interested in is that if I apply an external stress on this laminate, what kind of strains and curvatures are produced in the laminate, and then also what kind of strains and stresses are experienced in such a situation at each layer of the laminate. So that is what we are interested in finding, and that is what we will develop over the course of this week. We had done this exercise in a great detail in the introductory course, but for purposes of completeness we will again revisit this particular part of the course, and then from next week onwards we will move into advanced areas of composites. So the process for developing relations between stresses and strains at the laminate level is a three-step process. The first step will constitute developing strain displacement relations when the plate experiences some bending. So suppose we have a plate and we are trying to bend it. So when I bend it, I apply some bending force or bending moment, and when it happens, then the plate develops a curvature, and as it develops a curvature, it also experiences some strains and curvatures. So we will try to develop relations between these strains and curvatures and the displacement at each point in the plate. So we will develop strain displacement relations. The second step will be that we will link these strains with stresses at the level of a ply. So that is the second step, that we will develop stress strain relations at a ply level or at the level of a lamina, and finally we will develop relations between stresses and strains for the entire laminate. So this is a three-step process. So the first step is, as I suggested, that we will develop strain displacement relations. So this, consider this plate. So this is a laminate, it has several layers, okay, and let us say that this is my axis system X, this is the Y axis, and this is the Z axis. So the Z axis is going downwards, and the displacement in X is U, displacement in Y direction is V, and the displacement in Z direction is W. So if I consider any point and its coordinates are X, Y and Z, then once the plate bends, then it experiences a displacement which is U is a function of X, Y and Z, V is also a function of X, Y and Z, and W, which is the displacement in the Z direction, is X, Y and Z. So what we intend to do is that we want to develop relations between U, V and W. We want to relate these two strains in the plate, okay. So this is the problem at hand. Now before we start doing that, I wanted to make two things clear. Basically these are related to two assumptions which we make. Typically if there is a plate, consider a plate and it has several layers of composites. So let us say this is a book, and we can consider this book as a plate, and each of these pages we could consider these as a lamina or a layer of composites. Now, if I do not glue or bond these individual layers together, and if I bend the plate, so initially when I have the plate, let us say this is my x axis, this is my y axis, and this is the z axis. So, this edge of the plate is 90 degrees, this edge of the at the corner of the plate is at 90 degrees to the x and y axis, right, and it is parallel to the z axis. And if these layers are not attached to each other rigidly, then when I bend the plate, this axis also bends, and this not this axis, this edge of the plate is no longer at 90 degrees to is no longer, I am sorry, it is no longer parallel to the z axis. There is an angle which gets developed, and this happens when there is no bonding between the layers, So, and that so that is there, but if there is a perfectly rigid bond between all the individual layers, and then when I bend it, then this edge of the plate will remain parallel to the it will remain parallel, and it will remain the angle between this edge of the plate, this edge of the plate, and this edge of the plate, it will no longer change if it is rigid. So, and if there is not a perfect bond, if there is no bond, or if the bond is not rigid enough, then when I bend the plate, this angle between this edge of the plate and these other two edges of the plate, this will change, and as a consequence, if the bond is not perfect, so we will just note it down, if bond between adjacent laminae or layers is not perfectly rigid, then what will we have? We will have a shear strain, because each layer will slide over another other layer, and we will have shear strains gamma zx and gamma yz. They will not be equal to, so they will not be 0, so they will be not 0. Okay. Now, the theory which we are going to use is that we will assume that the bond between individual layers is perfectly rigid, and when that happens, so if the bond is rigid, then gamma zx equals gamma zy is equal to 0. These shear strains are called interlaminar shear strains. So, we assume that the bond between adjacent layers is perfectly rigid, and as a consequence of that, the interlaminar shear strain, that is the shear strain between two adjacent layers, is identically 0. This is one thing we will assume. So, this is something we are going to assume. And when that happens, when we assume that, then when the plate bends, so initially the angle between this edge and this vertical edge is 90 degrees, and when the plate bends, even then the angle between this edge and this edge still remains 90 degrees. So, this is an assumption, and this is, we call it the normality assumption. So, this is one assumption about plates. So, what we are developing is a classical lamination theory, a theory for classical known as classical lamination theory, So, this is the normality assumption. So, we make the normality assumption. The other assumption we make is that suppose this is a plate, and when I put some stuff on it, when I put some weight on it and I also apply some bending moment, then this thickness, the thickness of the plate, even after bending, it does not change. Okay. And if this thickness does not change, if this thickness does not change, and that is a realistic assumption, because when the plate bends, the thickness will not change, there will be curvatures and things like that, but overall this thickness is not going to change. However, if I load the plate on this side and also press it from this side, then the plate may get compressed, or if I pull it, then it may extend, but that is not happening. So, we are just putting some normal forces, and that does not lead to a lot of contraction or expansion of the thickness of the plate. And if the thickness of the plate is not changing, then remember our axis system is that in the z direction we call it W. So, if the thickness is not changing, then epsilon z, that is the strain, extensional strain in the z direction, is 0. Okay. So, this is another assumption, and this is called the inextensibility assumption. So, we are making two assumptions. One is the assumption of inextensibility, that epsilon z is 0, and the other one is the assumption of normality. So, from inextensibility assumption we assume that epsilon z is 0, and from the assumption of normality we come up with the relation that gamma xz and gamma yz, they are 0. So, these are the two assumptions, and using these two assumptions we will develop a theory for bending of plates, which is known as classical lamination theory. C, it is sometimes abbreviated as CLT. So, this is the theory we are going to develop. So, now we start developing this theory, and the first step in developing this theory is that we will develop strain displacement relations. Okay. So, we consider a plate, and when we look at it from the side, suppose there is a plate and I am looking at it from the end. So, I only see this surface, okay, and let us say this is the mid plane of the plate. So, this is the mid plane. So, remember it is not the neutral axis, it is the mid plane of the plate. So, if the plate is of thickness T, I have T plus T over 2 material up and T over 2 material down. So, this is there, and let us say this axis is x axis and my z axis is in this direction, okay. And I put some points on this. So, I put point A, B, C and D, and the distance between B and C is Z, and the overall thickness of the plate is T, and this is T by 2 and this is T by 2. Now, what I do to this plate is, so suppose this is the plate, what I do to this plate is I pull it, stretch it, and as I stretch it, the plate will experience a displacement in the x direction. So, that displacement is u, and I also bend it. So, it will experience a displacement in x direction and also a displacement in z direction, which is w. So, when I pull it and also bend it, let us say this edge AD, it moves out by some distance and it also rotates. So, this edge AD, so that when I bend it, the plate becomes something like this, okay. So, the displaced positions are A prime, this is the mid plane, B prime, this is the point C prime, and this is point D prime. Okay. And again, in the deformed configuration, this is the mid plane of the plate. And what happens is that I have pulled it outwards. So, the midpoint of the plate, which is B, it moves to B prime, and that displacement is called, let us say we call it U0. U0, okay. And U0 is a function of x and y, because it will vary from one point to other point in the plate. So, it depends on x and y. It does not depend on z, because U0 is the displacement of the point on the plate which is located in the mid plane, and mid plane is always located at z equals 0. So, it does not depend on z, but it can vary from x and with respect to x and y. Okay. So, the plate gets stressed by a distance U0, and also this thing plate is rotating, and as a consequence when it rotates, let us say this angle of rotation, this angle is alpha. So, it rotates by some angle. Okay. So, what happens to point C? The movement of the points, what is the, how much has point C moved by? So, movement of point C to C prime. How much is that moved by? It has moved by a total distance u, and u is a function of x, y and z, and that how much has, so again let us look at point C. C has moved to C prime. What has happened to it? It has moved out by u naught, but it because of rotation it has also come in by this distance. Let us call this distance delta. So, it has come inwards, it has moved out by u naught, and it has come inwards because of rotation by this distance called delta. And what is, we can calculate delta? Delta is equal to how much? It is minus z times sine of alpha. Okay. So, we can write it as z times sine of alpha, and if these rotations are not significant, they are not very large numbers, if alpha is a small number, then I can also write it as u naught x y minus z times alpha, because sine alpha is same as this thing. And we can also say that alpha, so what is alpha? Alpha is nothing but del w over del x. Okay. If you, how do I get this? See, if I look at this thing in detail, then what do I get? If I make a triangle in this area, then this triangle is something like this. So, this is alpha, this is delta x, and this is w or change in w. So, delta w over delta x is alpha, okay, if other things are constant. And again we are computing it this alpha in terms of mid plane deflection w naught. So, alpha is also a function of x and y only, alpha, because alpha depends on w naught, and w naught is the deflection of the mid plane of the plate. So, alpha depends only on the mid plane deflection of the plate. So, with that we can say that u x y z equals u naught x y minus z times del w naught over del x, and W naught is a function of only x and y. So, this concludes our discussion for today. Tomorrow we will extend this discussion and we will actually develop strain displacement relations, and please review this, and if you get confused please do shoot us emails, and once again we will meet tomorrow and we will continue this discussion and we will finally develop strain displacement relations for the classical lamination theory. Thank you very much. Bye.